Good morning, everyone.
Good morning.
I'm
Hello.
happy to take any questions that you have. Any questions?
What kinds of concatenation are there, and where should I be looking to have a better understanding of that? Like the properties of different kinds of concatenation, kind of.
Well, let's see. You can look at the, let me just pull up the slides to share with you. So let me just pull that up. So if you look at lecture 18,
Okay.
there's a discussion and a derivation of the different types of concatenations and how you can characterize their overall transfer function based on the component systems. So there's the parallel concatenation, the serial concatenation, and the feedback interconnection. So each of them you can, there's kind of a corresponding block diagram, and there's a derivation of the, you can express the output in terms of the impulse responses of the component systems. So in particular, for parallel concatenation, the overall impulse response is going to be given by the sum of the impulse responses, and the overall transfer function will be given by the sum of the corresponding transfer functions. And then for the serial concatenation, you can derive, just using properties of the convolution, you can derive the overall impulse response, which is going to be the convolution of the component impulse responses, and then the overall transfer function, which is the product. And then for the feedback interconnection, where H1 of S is the feed forward and H2 of S is the feedback component, the derivation is actually on the next slide, but what you end up with for the overall transfer function is that expression H1 of S divided by 1 minus the product of H1 of S and H2 of S, and the derivation is given here. And you can view the derivation again, either in the context of the, computing the output in the time domain. So in the expression in the time domain is a little bit more complicated because it involves convolutions with H1 of T and with the convolution of H1 of T and H2 of T. And then in the, that translates by taking the Laplace transform into this expression, which then gets simplified or written sort of more clearly, in this expression that was shown on the previous page.
Okay.
So that's really all you need to know about the basics of those interconnections.
Okay, thank you. I have one additional question on that. On the 2021 past exam, the second problem doesn't specify whether it's parallel or serial, and I'm not sure if I should be just assuming that or
Let me take a look.
I
This
can
is
send a screenshot in chat, I think.
uh,
That's easier.
either way. I mean, I can pull it up. This is the 2021 final exam.
Yes.
Which problem is it you're referring to?
Problem two.
Okay,
It's in chat.
problem two. Yeah, okay, let me just pull that up. Yeah, so for this one, you were given a pair of systems. And yeah, that would actually, at the time of the exam, I pointed out that it was intended to be a serial concatenation.
Okay, so would it if it comes up on this exam, would it be specified?
Yeah, yeah, and
Okay.
if for some reason in the wording of the problem I didn't make it clear, then I'll just make it clear during the exam. Yeah, I think in this case, the word was left out.
Okay, thank you.
Yeah, yeah, okay. Any other questions?
Yeah, I had a question on modulation,
Mm-hmm.
specifically um from the practice final from 2022.
Okay, pull that up.
Um, yeah.
Okay, and let's see, that was going to be um, problem number 3. Is that the one you're talking about here? Let's pull it up.
Yeah.
Yeah. Okay. All right. Which did you have a specific question? Which part of it?
Yeah, like part A. Um,
Okay. So let's just take a look. I think it's, let me just repeat the problem. So you're given a signal x of t, which is sine of 20t over pi t. So a sinc function. It's modulated using a carrier of cosine 30t. So that means that the resulting signal is the product. And then it's passed through a bandpass filter with frequency response that is basically lets the pass band is between frequencies between 30 and 50. And you're given that the output is called W of t. So that's the output of the bandpass filter. And then that is then multiplied by another carrier cosine of 40. And the result is then passed through an ideal low pass filter with gain 2 and cutoff frequency 20. And R of t is the output of that whole configuration. So the setup, let me see if I can actually draw this on my laptop. It'll be easier to do it on there. Give me just a second. Sorry, the laptop's just connecting so that I can draw on it here. So let me see if I can stop sharing this and go to the.
Huh?
Okay.
Yeah,
So let
I thought it was coming from downstairs.
let's see. Let's pull up that and then I'll just draw a quick schematic of what you're looking at just to make sure that that was clear from the problem statement. Okay. Okay. So let me try to get that schematic in here. Let's share the screen. Okay. So the setup is the following. You've got color that'll show up here. So you have x of t. Oops, that's not the one. Okay, here we go. So we have x of t, and that's going to be multiplied by cosine 30t. That produces y of t, which is then put through bandpass filter that looks basically like this, 30 to 50. And then that output of the bandpass W of t is going to be multiplied by cosine of 40t, and that then produces z of t, which is put through a low pass filter, and it has cutoff frequency 20. And gain 2. So this, if we want to just call it, this could be our H BP j omega. This is HLP of j omega. Okay, so that's the setup. And the output is this R of t. And you basically ask questions about R of t. And you're asked to express the result in terms of, so find R of j omega for a transform and express it specifically in terms of x of j omega. Okay, so now let's take a look. I'll just shrink that a little bit here. Okay. So, was there any particular step that you didn't understand? Should I just go through it step by step, or?
Um, so I was able to do the diagram,
Uh-huh.
but I think the second line I was confused about.
Okay, so for x of t, we just start out, and so you recognized what the transform of x of t was because it was a sinc function. So it's basically going to look like, just it's going to look like this. And the second line is telling you what happens when you apply the modulation of the carrier. And so it's going to shift that by 30. So I'm not going to draw it to scale here, but this will go to 30. And then it'll be 20 on each side. So this would be 10, and this would be 50, and then you'd have the corresponding thing over here. Okay. And then now is this where you were confused about this? Or
Yeah, yeah.
yeah, so
I
this,
was able to get everything else.
yeah. So I mean, what you can do is you can forget about that for the moment. Forget about the x tilde for now. You just can say what's the W of t going to be. So that's after you pass it through the bandpass filter. So when you look at W of j omega, what that's going to look like is, let me draw it over here to the side. The W of j omega, well, what we first do is we run this thing through the bandpass filter. So the bandpass filter is going to basically cut off, use a different color. So the bandpass filter is going to remove everything except from 30 to 50. So this is going to get removed, and this is going to get removed. Okay, so we just have left over from 30 to 50 and minus 30 to minus 50. And then we modulate that by, with a cosine of 40. So what that's going to do is, I hope this will show up okay. It's going to move that essentially by 40 to each side. So we have this will be 40 here, and minus 40. And so when you do that, when you shift to the right by 40, that's going to go to, way out here, you're going to have from 50 to 90, and then this is going to go, when we add 40, it's going to go from 30 to minus 10. But not all that's going to show up, right? So what we have is we're going to get this minus 50 to 30 is going to get from minus 10 up to 10. So that'll be the contribution from the minus, and I'm leaving off here I should put in the exact factors just as I'm drawing the picture. So when we first did this modulation, this was going to be, multiplied by half. Okay, now we do the modulation again. So this is going to be minus 50 to minus 30 is going to go to the minus 10 to plus, did I do that right? Yeah, it's plus 10. And this is going to be by, multiplied by 1/4. This 30 to 50 is going to go from, it's going to be way up here, 70 to 90. And then when we shift to the left, the 30 to 50 is going to go actually again to the minus 10 to 10. So this is going to end up, getting added another copy. And then we'll have some stuff over here on the sides. This was from 70 to 90. This will be from minus 70 to minus 90. And it'll be, by 1/4. Okay, so the thing that may be confusing is this use of the x tilde, and that's because this part right here, you were asked to express things in terms of x of j omega, but you see you've now basically created a portion of this transform that's kind of like a scaled version in the frequency domain of x of j omega. So x of j omega went from minus 20 to 20. So the question is, how can I represent at both of these? All of these are kind of scaled versions of this same transform that goes from minus 10 to 10 as opposed to minus 20 to 20. So we'd like to have a simple way of expressing that in terms of x of j omega. So the question is, how do you represent something that looks like this? In terms of x of j omega. Well, what you've done is it's the same. If I call that thing that has a 1 as the magnitude in that frequency range, basically what I've done is I've basically reduced the frequency axis, right? This is omega. I've scaled x of j omega along the frequency axis by a factor of 2. I've compressed it. So that corresponds to this response, which I've called x tilde of j omega. It's just like with a signal in time. If you compress the time scale, you multiply the time variable by a factor of 2. So here, this would be x of j 2 omega. And so now I can express this in terms of my x tilde of j omega. I could have expressed my w of j omega in terms of that x tilde. Also, you see, if I look at this was my w of j omega here. It's what I get by scaling, by taking x tilde of j omega, which is this scaled version of x of j omega, and shifting it to the right by 40 and to the left by 40 and scaling by 1/2. So I wrote that as 1/2 of x tilde of j omega plus 40 plus x tilde of j omega minus 40. So that, let me make sure that these arrows and things aren't confusing. So that's what w of j omega is. And so now when I multiply that by the carrier, which is cosine of 40, then, so this part I think should be clear now. This is the z of j omega is going to be just 1/2 wj of times w plus 40 plus wj times W minus 40. So it's going to be the thing we just computed. And if you look at what you get 1/4 of j omega plus 80. So this is, remember, this is going to be minus 80 and this is plus 80 here. So we get a copy of the x tilde of j omega shifted to the left by 80 and multiplied by 1/4. That's that first term right here. And we get the analogous thing to the right, shifted to the right by 40 and scaled by 1/4. And in the middle, we had the two copies that added up to basically exactly a copy of x of tilde of j omega times 1/2. And so that's what is the thing that goes into the low pass filter. The low pass filter is going to just pick out that copy of x tilde of j omega, which is from minus 10 to 10. The filter multiplies it by 2. So the filter is basically doing this. And then it multiplies by 2, so that scales it back up to being equal to 1. Because of that gain factor. So R of j omega looks like this now. Which is exactly the thing that we defined as the x tilde of j omega, which is x of j times 2 omega. So the catch was that it became a little bit difficult because of the effect of the bandpass filter to describe things directly in terms of x of j omega unless you did that scale factor. Because how do you express like a chunk of x of j omega easily? So that's why I just gave it a name, x tilde of j omega, which then could be expressed in terms of the original x of j omega ultimately. So that this became just x of j2 omega. Does that answer your question?
Yeah, thank you. Yeah, I guess I didn't approach it graphically at first. So I guess that just gave me trouble visualizing it.
Yeah, because the bandpass filter affects your copy of, it affects these copies of the shifted copies of x of j omega. So you need a way to describe them. So I would say as a general rule, when you're doing modulation, it's good to do both the equations and the figures. And because it's very easy to visualize what's happening with modulation. That's the nice thing about drawing the figures. It tells you the whole story. It's also important to express it, mathematically. And usually that's in the problems, you're generally going to be asked to do both, to give a mathematical expression and to draw some pictures, mostly to help you make sure you're visualizing things correctly and that your equations kind of are consistent with the drawings. But yeah, in this case, drawing the figure was kind of essential because it let you recognize, or it gave you a way of, you could have drawn the pictures without expressing it mathematically all the way down to the very end, and then notice that, hey, the thing that you get at the end isn't really x of j omega, it's the scaled version in the frequency domain of x of j omega. And then that could lead you then to realize that what you're really dealing with all along throughout the process after you go through the bandpass filter, you're dealing with basically operations on that scaled version of x of j omega. And so if you give that a name, then you can write down the equations and so on. So that was kind of the idea. Now in the actual version of the statement of the problem, it just said determine the Fourier transform. So it didn't expect you to necessarily write down all, in that case, you're not asked explicitly to write down all of the mathematical equations, partly because I wanted people to be able to state the correct answer, even if they didn't do equations all the way, but just kind of understood conceptually what was happening as reflected in the figures. And so if you did end up getting to this final stage just by using the figures, then your only issue would be, how do I express that in terms of x of j omega? And that was really just using the, scaling property of, a function of omega, that if you compress the function of omega, then you're really multiplying the argument by 2, the frequency argument by 2, because you've scaled it by half.
Okay, I think that makes sense. And then you'd
Okay.
say to just apply the same process to just any modulation problem that we encounter. Like
What
just
do you mean by employ the same process? Because the
like
modulation, the
just
problem may be
Mhm.
different, in terms of.
or just yeah, like what is it? Maybe kind of draw out what's happening in terms of like how the signal is affected um based off of like the type of filter that we're given, and then just try to represent it mathematically.
Yeah, I mean, you kind of know mathematically what happens when you multiply, when you do the actual modulation, right? That's
Mhm.
multiplying by a cosine. So we know exactly what happens in the, in the frequency domain. We can write it out very explicitly. That's really what this equation right here is doing. Right, that's the first step, the modulation step. So that we know, but it's when you start doing stuff to those signals, like putting them through filters or modifying them somehow, then it might become a little bit, depending on what happens, it might be a little more complicated to express it in terms of there's the original transform. But drawing the pictures can always, we know exactly what happens when we, apply a modulation step. We know in terms of graphically, which is what we drew here, we know exactly what happens when you put it through a filter. We know if we have the frequency response of the filter, we know we just multiply that by the frequency response of the signal. So that's what we did here. And then here there was another modulation step. Again, the modulation step is just a straightforward, it's the same thing every time. But now you're applying it to, the output of the filter. So the answer is, yeah, draw pictures, definitely, to help keep track of what's going on. And very often you'll be asked to draw the pictures, depending on how the problem statement.
Okay, thank you.
Mm-hmm. Any other questions?
Yeah, I have a couple general, like not specific to any problem questions, if that's okay.
Sure.
So this is a very, very stupid question, but what happens when you take the reciprocal of the transfer function? Like, does that have any properties associated with it? Is that how you get the inverse of the system?
Well, yeah, it's true that if you look at the that's a good question, actually. If you look at the let's say we pull up the the table of because you're really asking something about properties of the Laplace transform when you ask about the transfer function. So let's take
Yeah.
a look at what the properties of the what we can say about the properties of the Laplace transform. So so let's go to that table from chapter 9, which gives us, I have to flip it around, so just give me 1 second. So here are the properties of the Laplace transform. And what we see is that the convolution property is very similar to the convolution property that we had for the Fourier transform.
Mhm.
It says if you take the convolution of two signals, then Laplace transform of their convolution is the product of their respective Laplace transforms. You have to be a little bit careful about the region of convergence, but you know it's going to contain the intersection, because it's going to sort of contain the points where both x1 of t and x2 of t, have their Laplace transform integral converge. It could be more, just as we saw in some cases, there's can be sort of cancellation of poles and things going on that allow you to get a larger region of convergence. So that's what this is saying. So now, if you suppose you had two systems, and you had, let's say you had in one system, you had, let me just pull up a whiteboard here I can write on. So now suppose you had, two systems that, you had S1 and S2. S1 and S2. I'm not sure why this isn't writing well. And let's say this one had, impulse response H1 of t. So these are LTI systems. And H2 of t. And corresponding transfer functions H1 of s and H2 of s. Then if you had the fact that let's say that S1 and S2 are inverse systems, so they're inverses of each other, then what we would know is that this configuration would describe that relationship. We would have, we did a serial concatenation, then we know that this overall system would be the identity. So this overall system is the identity system. So we in particular know that because it's the concatenation, the serial concatenation, we know this is going to be H1 from that property we just looked up. It'll be H1 of s times H2 of s. But we know that the overall system is the identity system. And so that means that the overall impulse response is the unit impulse, and we know that its Laplace transform is just equal to 1. So now if you look at this, then you could say that H1 of S is equal to 1 over H2 of S. So yes, in this case, you could say that 1 over H2 of S, or 1 over H1 of S, is the transfer function of the inverse system. So yeah, the answer to the question is yeah, that makes sense.
Thank you.
Okay.
That makes sense.
Mm-hmm. Good question.
I have another question if no one else is going to ask one.
Okay, go ahead.
So, uh, like stability and region of convergence stuff.
Mhm.
So if a system has all of its poles on the like imaginary axis, is it
Mhm.
stable? Is it like halfway stable?
So so strictly speaking, the way we define stability, um, that would represent an unstable system, because um, the impulse response would not be, uh, absolutely integrable. But it's also sort of what some people, if you remember from the video that was shown in class,
Yeah, that's why I'm
it's
asking.
it's also, some people refer to it as marginally stable. So
Right, okay.
let me just pull up so yeah, so it's partly terminology is what's the issue here. We saw in the lab, we saw in lab 5 that in one of the cases that you looked at, and that you actually looked at the impulse response. So this is when we were looking at the case of just proportional feedback, and we saw that the poles that we got, sometimes they were on the imaginary axis, for different values of K. So they were like symmetric pairs on the imaginary axis. And what we saw is that this is what the impulse response looked like.
Mhm.
So this was for K equals 10 and K equals 20, which I think, we're going to be like these points, 10 corresponded to these guys, and then 20 corresponded to these guys. And they were, separated by 2.5 in terms of the K value. So, along for each set of pair of points. So the bottom line is this is what it looked like. So you ended up getting an impulse response that looked like something to do with a sinusoid. So specifically, it was again, by referring to the table, when you have those kinds of transfer functions. So the transfer functions look like this: 1 over s squared plus something. Then it turned out that the square root of that something is the fundamental frequency of the resulting impulse response, which has the form of h of t is 1 over omega naught sine of omega naught t times u of t. So it's kind of a one-sided sinusoid. And I don't know if you can, let me blow that up a little bit just to make that a little clearer. So that's what's going on there when you have that situation. When you have the situation of poles that are on the imaginary axis. In this case, it's for this particular transfer function. If it was a more complicated transfer function, then you'd have to sort of, break it up using partial fraction expansion and so on. But but you may end up with some of the terms in the partial fraction expansion that look like this. And, that's really referring to the, specifically in the table of the pairs, the transform pairs. For the Laplace transform, we saw there was something in the table, there was a particular case, which was 1 over right here. It was this guy
Yeah,
right
12. Yeah.
here, right there. And that's what we used. And if you get other ones, then you could get other expressions, so like if you get something that looked like s over s squared plus omega naught squared, then you'd have a cosine instead of a sine.
I guess my question is like a sinusoid is bounded, but is the system still considered unstable?
Yeah, it depends. Again, it's a matter of the terminology. It's unstable because we typically say that the system is stable. We want to see that a bounded input produces a bounded output. But if you have a cosine as your, a one-sided cosine as your impulse response or a sinusoid, you can come up with, you can come up with inputs that will, when you look at the bounded input, that can produce an unbounded output. So that's why, what it means is that this thing is not absolutely integrable, right? If I take the magnitude of the sinusoid, right, take the magnitude of a sinusoid. So here's what we want to know. We want to know, is it true that the integral of h of t dt from minus infinity to infinity, we want to know if that's just a finite number or does it blow up. But if I take the integral of a sinusoid, think of this one-sided sinusoid. So here's 0. So it's 0 to the left of 0. But then, the sinusoid kind of looks like this. And it just goes on forever. So if that happens to be my h of t, my h of t is of the form, let's just use the form that we had, in this formula here, just sine of omega t, because in our answer we had a scale factor just because of the form of the transfer function. But in general, it would be sine of omega t, omega naught t times u of t. Now, if I try to integrate the magnitude of that, so the magnitude is going to rectify that signal. It's going to look like this.
Okay.
And if I take the integral of that, that's going to blow up.
Yeah. Okay.
Yeah. So in this case, the integral of, sine omega naught t u of t, the magnitude, that's actually not going to be a finite number. That's going to turn out to be, that's going to be infinite. And so that's why we say that it's not stable. We say it's marginally stable because it's kind of on the borderline. It's not, it's not giving you something where the impulse response looks like this. It's kind of marginally well behaved, but it still has this property that it doesn't satisfy the bounded input, bounded output condition. And you could see, if you saw, in that, the reason we say it's marginally stable is, where people use that is because you saw in that video, when he, when you have the parameters, so that's where your poles are, it sort of leads to, it could lead to this sort of oscillating behavior. it doesn't drive the angle of the pendulum to zero. It just keeps oscillating back and forth. It doesn't really converge to anything. But on the other hand, it doesn't just completely behave in an unstable way and cause it to collapse, to fall down.
So it's
So it's a matter
unstable
of
but teetering.
terminology is what it is, really.
Okay.
Yeah.
Do
Does-
we work through the 2018 final?
2018 final?
Yes.
Which problem?
Can we do problem 4?
Sure, let me just pull that up. Okay, let's see. 4. That's the amplitude. Oh, that was also amplitude modulation. Is that the one you're asking about?
Yes.
Yeah, okay. Okay. Which part of it? Do you want us to go through the whole thing or?
If no one minds, yeah.
Okay. So here's, you're given you're given basically a band limited signal. So this is just, a schematic. If you preferred in your, mentally for this problem, you could, initially you could just consider it as talking about a signal whose, Fourier transform looks like that, for all intents and purposes. It was just to make it general. And so the idea is you're going to use amplitude modulation to transmit it. You're going to multiply by this carrier signal, cosine of 3w over 2 times t. So this signal has, the original signal is band limited to minus w to w. So that we kind of know what goes on there. But then something gets added to it, and x2 gets added, also band limited, but it is multiplied by a carrier that's sine of 3w divided by 2 times t. So what you end up with is this is your total transmitted signal. Okay, so that's kind of the initial setup. And now what you're asked, you're given some identities that'll be used later. So now you're asked to express the Fourier transform of the output in terms of x1 of j omega and x2 of j omega. So that's just a straightforward application of, what happens when you multiply a signal by a sinusoid. And so in this case, the two components of the signal, you've got, this is the component that corresponds to x1 of t times cosine of 3w over 2 times t. And this is the piece that corresponds to the x2 of t times the sine of 3w over 2 times t. Okay, so that is just the first part. Was that part okay?
Yes.
Okay, so that's kind of the first part. And now you're asked when you're at the receiving end, you have a demodulation circuit that first takes that output that we just computed the transform for and multiplies it by that same c of t. So this is going to be y of t times the cosine of 3w over t, 3w over 2t 3W over 2 times t. And that's your z of t. So that's the first thing. And you're asked to write an expression for the demodulated signal. So it's just going to be, this is just kind of multiplying it out. You know, this is kind of like a step-by-step leading you through the problem. Now, the catch is that you now have c of t times c of t and s of t times c of t. So this is the cosine times the cosine and the sine times the cosine. This is where you use the identities that were given to you. And the identities were that when you take the product of cosines, cosine squared, you get 1 plus cosine 2 theta over 2. So we'll be using that identity. And then we'll be using cosine times sine, which is sine of 2 theta over 2. So that's what's used in this next step here, just to take that product of the cosines and represent it as 1/2 times 1 plus cosine of 2 theta, where here the theta is 3w divided by 2. And so 2 theta becomes 3w. Okay, so that's the cosine times cosine. And then this is going to be the sine times the cosine. You're going to get a factor of 1/2 times sine of 2 theta, which is sine of 3wt. Okay, so that's what we've got there. Now, next step is just expanding it out a little bit. So there's nothing, you know, no identities or anything are being used here. This is just writing that out. And then you're asked for the transform of that signal. And so you just apply the transform to each one of those components. And you say, well, the first piece is 1/2 x1 of t. And so we're going to get 1/2 x1 of j omega. The next piece is where we have, I'll just use some different colors to highlight it. We've got the transform of 1/2 x1 t cosine 3w. Well, that's just modulation again. So we know that x1 of t cosine of 3wt is going to lead to 1/2 x of j omega shifted to the right by 3w plus 1/2 x1 of j omega shifted to the left by 3w. But in addition to the factor of 1/2, we have another factor of 1/2 in front, so that becomes 1/4. So that's, again, just kind of using the general expression for what amplitude modulation does to the transform of a signal, what it does in the frequency domain. And then for the other case, it's just kind of analogous, but now we're doing with sinusoidal rather than cosinusoidal modulation. And so we know we're going to get, it's going to be 1 over 2j times the shifted version of x2 of j omega shifted to the right by 3w, shifted to the left by 3w, but with a minus sign in front. And the 1 over 2j also gets multiplied, so we're dealing with this term. We've got that 1/2 in front, so it becomes 1 over 4j. Okay? So it's really all multiplying by cosines and sines and seeing what that does in the transform domain. Okay, so that's the second part. Is that clear?
Yes.
Okay,
Yeah.
so now let's see what happens when we move on. Now it says that signal z of t that we just computed the transform on is put through a low pass filter with basically a cutoff frequency of 3w over 2 and gain 2. And we want to see what we get for the output. So if we look at so there are pictures shown here, but if we look at this expression that we computed for z of j omega, what we see is that we have a term which is just, you know, x1 of j omega with a scale factor. So that's going to be something that kind of lies in the region from -w to W. Then we have copies of x1 of j omega that are at 3W and minus 3W. So again, I'm going to just use, for convenience, I'm just going to use the triangle rather than that fancy looking thing. And we have a factor of a half in front. Then we have these guys, which look like the x1 of j omega, but scaled by a quarter. So here's 3W. And let me just make sure as I'm doing this, let me just double check one thing that I'm solving the right problem here. Yeah. So let me finish drawing that picture, and then we'll put it through the low pass filter. I'll put in the low pass filter at the end. So it's going to be, minus, so j omega minus 3W and this is going to be j omega plus 3W. These are going to be scaled by a quarter. And then we also have the stuff, for the, probably should have drawn those in green just to be consistent with the color scheme I was using. Then we have, so that took care basically of these terms right here. And then what we're left with is we have this component, these guys. So these, it's going to be 1 over 4j, but again, it's copies of x2 of j omega, whatever that happens to look like, but it's band limited, again at 3W and minus. So that might be, I'll draw them underneath, even though they might be, so this minus, this 1 over 4j is complex. So in a way, we can't really draw it exactly on here, but because conceptually, the 1 over 4j is going to be the same as negative j over 4. So if I wanted to, I could draw something like, this thing, and it's, negative j over 4. And then there'd be a copy over here, which, it has a minus sign in front. So, it's going to be something like, whatever, something like that, plus j over 4. But the bottom line is that when we throw in our low pass filter, remember the low pass filter was at minus 3 pi over 2 and plus 3 pi over 2. So that's actually going to be right here, because these guys, this is minus 2W here, and this is positive 2W. So it's going to be right in that ballpark, and it's going to filter out those frequencies. And its gain factor, I forget what it said, but I'm assuming that it was 2.
It was 2.
So it was going to be 2. And so what it's going to do is it's going to exactly compensate for the factor of 1/2. And so what the conclusion is that at the end, you get exactly x1 of j omega. Then it asks, how would you recover x2 from y of t? And so now you're going to use the fact what happens, there's the other identity that we had, right? So we had 3 identities. We had that, get rid of all this drawings. So what we used so far was we used what happens when you have cosine squared and sine times cosine. That's what helped us solve that problem. The remaining identity is going to be sine squared. And that's the one that gets used in answering the last part of the problem, because it asks you, how could you recover the sine portion? And actually, before I move it, let me go back. If you focus on that particular one, that particular identity, what you see that it does is, see, what we saw when we used the cosine squared is it gave us that copy of x1 of j omega, with some scale factor right where it should be in the frequency domain, and then copies on the edges, the outskirts that ended up getting filtered out. The cosine times the sine gave us copies of the x2 over there on the fringes, but nothing in the middle. So it was really, we were taking advantage of the fact that the cosine squared gave us this 1 right here. It's really 1/2, but that's the scale factor. Gave us the copy of the original. So when you multiply by sine by sine, you're again going to get a 1 there, which means you're going to get a copy of x2 in the middle. Plus some stuff that's out here at 2 times the carrier frequency, which is going to be 3W again. And then when you multiply that by the cosine, you're going to use this identity again. It's going to only give you copies of x1 over on the fringes. So it's really the same game. It's just we're, reversing the roles of cosine and sine. And so what you end up with, if you go through the exact same type of calculation and drawing those figures, you find that if you multiply by sine instead of cosine, it just kind of reverses the roles. All right. Sine of 3W over 2 times t rather than cosine of 3W2. You apply that to the signal y of t and use the exact same filter as before. You're gonna pull out a copy of x. You're going to see a copy of x2 of j omega in the frequency domain, which means that the signal in the time domain, what you're seeing is x2 of t. That make sense?
That makes sense, yeah.
Okay.
And then we apply the low pass to get it.
Yeah. So you have to use the same, it says, apply the resulting signal to the input of the same low pass filter that you used up here. And that was this guy. Cutoff frequency 3W over 2 and gain 2. Okay. Any questions on that? Anyone?
I have a question.
Okay. Yeah. This one on this problem?
No, not this problem.
Okay.
I have a question on the 2024 final.
2020, which one?
Final problem 3.
Okay, 2020. All right, 2020, problem 3. Also amplitude modulation. Is that it?
I have a question on the part B, the demodulation. So the answer shows that we can demodulate by multiplying a cosine. So how do you know that we can get the signal back after a bunch of modulations and filtering?
So in this case, it's from the particular figure, from the particular signal. So here you were given a very specific signal with a given transform, x of j omega. And after going, this is actually the same problem, one of the ones we did it was in one of the clicker questions, I think. And the question is kind of, what do you end up with? the outputs. So in this case, it's related to that clicker question. It wasn't exactly the same. But you end up with this as the thing that you're dealing with. So this was the transform of the y of t. So this was, the y of t is what came out after you did modulate, you went through that filter and so on. The y of t was the signal that was right out at this point in the diagram. It was the output of, running the original signal through this kind of phase shifter, modulating with a sine of omega naught t, taking the original signal, modulating with cosine of omega naught t, and then adding those two things up. So that's the output. And so it looks like this right here. So the question is, how do you get back? We're trying to recover the original signal. Well, the original signal had as its transform something that looked just like this, except, the pieces were rearranged. It was like this instead of the what we see for y of j omega. So this was our original x. I guess we were calling it x of j omega. So the question is, how do we get that back? So this requires kind of making an observation that, well, I could get it back if I shifted this guy on the right to the left by omega naught. And I shifted this guy on the right. Sorry, this guy on the left to the right to give me, this. I haven't drawn everything to scale, but just to give you a rough idea. Okay, so that's the kind of the observation. So the question is, what do we know about how you can do things like shifting signals transforms to the left and to the right? Well, we can do it by doing modulation. Now, if we do modulation, we have to shift the whole shebang. So if we shift this guy to the left by omega naught, then we have to shift this guy to the left by omega naught. So we're actually going to get a copy over here. Let me put in some colors to kind of help keep track of what exactly is going on. If we multiply by cosine of omega naught t, what we know happens is that we get a copy of this whole thing shifted to the left by omega naught. So this is going to end up giving us that. That's kind of the shifting to the left. But we also know that we're going to get a shift of it to the right. So this is going to end up giving us that. And then we'll have, over here at 2 omega naught, when we shifted this piece to the right, it's going to actually look like that. But the bottom line is what we end up with is those three components of the resulting transform. We have this, we have this, and we have this. And this part in the middle looks, again, we have to be careful of our scale factor. Everything gets multiplied by a half. And because these don't overlap, we don't get when we get the overlap, you double it, but here they're not overlapping pieces, they're separate components of the spectrum. So everything's multiplied by half. But if we now take a cutoff filter, a low pass filter with a cutoff frequency that's in between, it falls in these gaps, so this one right here is what we called omega sub m, I guess. That was the maximum frequency of the signals transform. And this is minus omega sub m. So if I pick a cutoff frequency that's between omega sub m and omega naught minus omega sub m. I can carve out that part of the transform, multiply it by, have a gain factor of 2, I'm going to get exactly back the original x of j omega. And I wrote this wrong. I wrote this as omega 0. That was the carrier frequency. These should be omega sub m. That was the. So it's going to be exactly just like this guy right here up above. So that's how you can, that requires some, familiarity with what modulation does to the transform. But once you recognize that, you realize that you can just use that same cosine omega naught t as the demodulation factor. Does that answer your question?
Yeah, that answers the question.
Okay, good. Let's see, there's some things in the chat. Let me see if anybody had a question in the chat. I think we got to everything in the chat, it looks like. Did we or not? Yeah, we did. Okay. Any other questions?
I have a quick question.
Sure.
Would we have to worry about anything regarding the Z transform in the discrete time domain and regions of convergence for the final, or is that not going to be there?
No, that won't be on it.
Perfect.
Yep.
Thank you very much.
Yep.
I had a question on the sampling theory problem. So
Mhm.
problem 4 on 2022 for the practice
2022.
final.
Okay. 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 And I think I should point out that this particular final was, I think, let me just see if that's correct, that this one was a little bit different, or was it a different one? Yeah, this one was a little bit different. This particular exam was different because this was, we were still, there were still some issues kind of relating to recovering from COVID, I think. And so anyway, the bottom line was that the test was it was multiple choice in the sense that, there was still partial credit given, but people weren't expected, they weren't asked, to draw figures and things like that. So this was like a little bit of a fluky year, that kind of things came up that made this format be something that some professors had suggested using, but I haven't done it since and don't plan to. But just so you're aware, that's why you don't see as many drawings and things in this one, and there aren't questions asking you to draw sketches. But for your exam, it'll be kind of a more related to the other exams that you've seen, where you might be asked to draw a sketch, just like on the midterm. I just thought I should point that out. Okay, so this one, here's the sampling theory problem. So you're given a signal with, band limited signal with maximum frequency, W, and you're asked to determine the minimum sampling frequency required to avoid aliasing and allow reconstruction from the samples for these signals obtained from X of t. So it's really, this is a standard type of sampling theory question where you have to figure out what the maximum frequency of this new signal y of t is. So it's using properties of the Fourier transform, really. So the first one was y of t is x of 3t minus 1 squared. So this involves several operations. So first thing you do is you're transforming the time variable, and then you're squaring the signal. So if you first look at the part that involves transforming the time variable, it's x of 3t minus 1. So what that means is you shift by 1, and then you scale by 3. Right? That's x of at minus b. So you're going to shift by b and scale by a. Shift by 1 and scale by 3. So let's do it step by step. Let's just do the shift by 1, x of t minus 1. Well, we know what time shifting does in the transform domain. It's just from the time shifting property in the table, and it's going to be e to the minus j omega x of j omega. Now, if we think in terms of, magnitudes, places where the transform is 0, we know x of j omega is 0 outside of the band minus w to w. If we multiply by e to the minus j omega, that's not going to change where the result is equal to 0. So this thing itself is still going to be non-zero in the range minus w to w. It's not going to have any non-zero values outside of that. So that's just kind of a preliminary observation. But then we take that signal and we scale it by 3. So the scaling property says that when you scale by 3, the result is you multiply by 1/3 and you scale the frequency argument by a factor of 3. Divide by 3. So if I take what I had up here for that first, intermediate step, that was what I got when I shifted by 1. Now I scale it by 3. I'm going to end up with this thing right here. One-third e to the minus j omega over 3 times x of j omega over 3. So again, the question is, where is that going to be 0? That's really what you're asking. And this j omega over 3 means that we stretch things out, right? So that it's going to be from minus 3w to 3w. That's going to be the region where it could be non-zero. It's actually not going to look so weird, probably. Let's assume we're dealing with one of our typical guys, might look like that. So when you have that, that's kind of the x of j omega over 3 part. That's this guy. But now you have this. But once again, you look at that and you see, well, that's e to the minus j omega over 3, right? That's going to be some point on the unit circle always, whatever omega you put in there. And, it's multiplied by 1/3, but you're not going to get any non-zero stuff outside of this range. So it's going to still be kind of limited to minus 3w to 3w. And you can kind of see that also. What's done here in the solutions is it says, well, let's look at the magnitude. And that kind of takes care of that e to the j omega, e to the minus j omega over 3 stuff. It's basically 1/3 times the magnitude of this stretched version of x. And so again, the conclusion is, the bottom line that you're trying to get to is that this z of j omega has the property that it's 0 outside of that band minus 3w to w. So it's band limited, and that's its maximum frequency. And now the next step is we square it, right? We have to look at the square of, so y is now, y of t is actually going to be z of t squared. And so z of t squared now, we want to know what's that Fourier transform. We're going to use the multiplication property. So it's going to be z of j omega convolved with z of j omega multiplied by 1 over 2 pi, which turns out to be, given by this right here, based on what we had before. We're just plugging in z of j omega, in for these two terms. And that's the convolution of those guys. But we said that what that looks like is we're really convolving something that looks like this with itself. And we know that when you do convolution of two band limited signals, the maximum bandwidth, it becomes the sum. So we know that y of j omega is going to be 0 outside of, so that's going to be this convolved with this, kind of with itself. So we know that's going to end up giving us something that is going to range out to, 6W minus 6W to 6W. And so that now becomes the corresponding maximum frequency there for that y of j omega. So it may look something like, like that. And so now we know if we want to reconstruct that after sampling, we better sample it, at least 2 times our omega max. This is our omega max for y. And so that's going to be 12. Any questions on that? Is that clear?
Yeah,
And
I
then this,
think that makes sense.
okay. And then the second part is just, again, another exercise. In this case, it's going to be exercise in using the properties and the transform pairs for the Fourier transform. So in this case, we started out with x of t, but now we convolve it with sine of 2wt over pi t. But if we so let's rewrite that as x of t convolved with z of t. So we call that sinc function z of t. Okay, and so now we use the convolution property. It's going to be the product. But first we want to figure out, again, x of t, we're assuming just, x of t, x of j omega looks something like this, let's say, minus w to w. And then z, what we know from the table, we know that z looks like, if we just have to look at what its, argument is, it's 2 times w times t. So that's going to look like this. That's going to be our z of j omega. And now the convolution property says that the convolution time domain becomes product in frequency domain. But now if we take, this is a 1 here, let's assume that's a 1. Doesn't have to be, but the point is that this is the thing that we're multiplying x of j omega by. We're multiplying it by this, c of j omega. So it just multiplies by 1 in the range minus 2w to 2w. Well, it's just going to give us a copy of x of j omega again. Because x of j omega is 0 outside of minus w to w. So all of this part of, this part of the z of j omega is kind of irrelevant because x of j omega is already 0 there. So it doesn't matter that this is 1. It's just being multiplied by, it's being multiplied by 0. So only part that really matters is what's going on between minus omega, minus W and W, which is like this region right here. And there, everything just gets multiplied by 1. So we just end up with, as our result, x of j omega. So that means that the resulting signal, y of j omega, or y of t, has a y of j omega that looks just like x of j omega, which means that the maximum frequency is, again, W. It's 0 outside of minus W to W. So again, the Nyquist criterion says we have to double that at least. So we conclude that we can reconstruct it if we sample at a frequency that's at least 2 times W. And I think that was it for that problem. Were there any questions on that? Is that clear?
Yeah, that makes sense. I think I had trouble on B, but yeah, I think the explanation helps
Okay.
me a lot. Thank you.
Okay, sure. Okay. Anything else? Any Laplace transform questions? Kind of touched on most other things, but or discrete time things, discrete time Fourier transform. It might be good to look at something, on there. So, I mean, if we want to look at the 22 final.
I actually was a little bit confused about problem 4, the one you were just going over. I was wondering where z of t came from in part B, like what the purpose of it was.
Let's see, which year was that one we were just looking at? Is it 20?
All
20
2022.
2022? Yeah. So the z of t, that was just the name that was given to a signal for convenience, right? It's just, see, x of t was convolved with, we took our original x of t and we convolved it with something. The something was a sinc function, sine of 2w of t divided by pi t. I just gave a name to that so that we could more easily talk about it. I just called that z of t, so that y of t became x of t. This is kind of what I wrote at the beginning, just to kind of clarify the format of this way in which we're getting the new signal. The z of t is just the name that I gave to that sine of 2wt over 2t, right? It's just this guy. So the convolution, it just became x of t convolved with z of t. That's all that the z of t was. It was just giving a name to that signal that we were convolving with. Does that make sense?
Yeah, that part makes sense. So if I had z of t where it was sine of wt, then the z of jw, that would range from negative w to positive w, right?
If it was just a sinusoid, then the transfer form would just be something that goes, looks like this. Yeah.
Yeah, sorry, not just a sinusoid, with the pi t underneath in the denominator.
Oh, yeah. If it was just W as opposed to 2W, that's right. It would be, because if you look at the transform pair that we're working with here is, just one of the, just straight from the chapter 4 tables. So I'm just pulling right off of the continuous time Fourier transform pairs. I'm just pulling off, where is it? I went too far. The basic Fourier transform pairs. I'm just pulling off this one right here. That's the sinc function in the time domain. just right here. This is all I'm using. And if it's sine of whatever it is, sine of some frequency times t, then it's going to be a brick wall transform between minus w or minus that frequency and plus that frequency. So in that particular problem, the w was 2w, and so it went from, it was 1 from negative 2w to positive 2w. If it had just been w, then it would be just like this, between minus w and w.
So x of jw also ranges from negative w to w.
Right, in that problem, that's right. It ranged from minus w to w.
And so
That
if I
was,
multiplied that by z of jw in the scenario where z of jw also ranges from negative w to w,
yeah,
wouldn't that also get you y of jw?
yep, it would.
Okay, yeah, so I guess then
It
I
would give you
just
the same output. If what you're
Yeah.
asking is, was it give you the same output? The answer is yes. It would give you the same output.
Could you go over how the logic of the like where the logic of the last few sentences comes from, like the ws greater than 2 w max?
This,
Yeah,
when you say the logic of it, what do you mean? So the w
like
max is, the w max of y is w, or the omega max of y is w, right? That's what this told us.
oh, so we're just doing the Nyquist rate like rule.
Yeah, this is just applying. Once you figured out the omega max, once you figure out the omega max, then you just apply Nyquist. There's nothing special that needs to be done after that. You just apply the Nyquist criterion, which says you have to at least double that with the
Okay, got
sampling
it. Yeah.
frequency. Yeah.
Sorry, I thought the 2 times w max was somehow like related to the 2 times capital W with
No,
C of
this,
JW. Yeah.
yeah, this is just the general kind of jargon to refer to the maximum frequency of whatever signal it is that you're trying to sample. So in this case, it's y that we want to sample. And so this omega max was supposed to be the maximum frequency of the y of t.
Yeah. Okay. That sounds good. Thank you.
Okay.
I also have another question on that problem really quick. I guess I understand most of the reasoning and things
Mhm.
like that, but in in the cinch definition, in the cinch to the z of jw from table 4.2, it said, like it's 1 for w being less than 2w or omega being less than 2w, and then like that table, right? How again did I get this from the table? How again did we get it so that the w is only positive if it's less than just w? Like if you go back to the problem, it's like
Yep.
yeah, it's like, how do we do it again? That x of j
Well,
equals
so
0 for
x,
just greater than w? Yeah.
yeah, so x looked like this. X of j omega looked like this.
Mhm.
Right? This is our x of j omega.
Mhm.
Because it was 0 for frequencies larger than w in magnitude. So it looks something like this.
Mhm.
Z, we said, looked like this. Z looked like from minus 2w to 2w, it was equal to 1, like this. Okay? And we're taking the
Right.
product of these two signals. That's the thing to keep in mind here. It's the product because these signals were convolved. The signals weren't multiplied together, they were convolved. That means in the frequency domain, we take these two pictures, x of j omega and z of j omega, and we just multiply them together at every frequency. At every frequency, we take the product of those two transforms. Well, between minus w and w, z of j omega is equal to 1. So that means we're just going to get, it doesn't affect anything in between. We're going to multiply x of j omega from minus w to w. That's going to be multiplied by 1. It's going to look just like x of j omega.
Okay, that makes sense. So
But outside of that region, z of j omega is still equal to 1, but x is equal to 0, right? Over in this
Mhm.
region, we're multiplying that 1 from the z of j omega. We're multiplying it by 0 from the x of j omega. That means we're going to get 0 out here. And we're going to get 0 everywhere because z of j omega is 0 outside of minus 2w to w, and also so is x. So we're going to be multiplying 0 times 0 in that region. So we're going to get all zeros out there. So all we get is just a copy of x of j omega.
Right. Okay, that makes sense. I didn't realize that the way we figured out for x of j, w being 0 for w being greater than w, or like the limit of negative omega to omega would be from the original signal. So okay, that makes sense. And then yeah, the omega max is because it's for y of jw, right? So it's only 0 between negative omega and omega.
Yeah,
So
because this is
okay,
my y of j omega now. After I
yeah.
took the product of those transforms, it looks exactly like x of j omega. So it's going to be 0 outside of minus w to w.
Mhm. Okay, that makes sense. Thank you.
Okay. Okay. Well, maybe we should look at one that nobody's asked anything about discrete time, which is probably a worthwhile thing to be looking at because it is going to be on the exam. So here's somebody did ask about this question, just what the terminology meant, but this was a case of a concatenation of two discrete time LTI systems. They're first order non-recursive systems, and you're asked to find the frequency response. And then you're asked about inverse systems. And then you're asked about putting an input into the inverse system and seeing what the output is. So in this case, you just apply the discrete time Fourier transform to both sides of this equation. You have two equations. You applied it to both sides of the equations. That's going to give you y of e to the j omega, and then the x becomes x of n transforms to x of e to the j omega. You have to use the time shifting property of the discrete time Fourier transform, which means you're going to throw in a phase factor. So you get y of e to the j omega is equal to x of e to the j omega minus a half e to the minus j omega. That's the phase factor times x of e to the j omega. And then for the second system, you're going to get the same thing, but with minus a quarter times e to the minus j omega, x of e to the j omega. So when you solve for y of e to the j omega over x of e to the j omega, you get these two expressions, 1 minus 1/2 e to the minus j omega, and 1 plus a quarter e to the minus j omega. Okay, that's just by taking these expressions, something like this, dividing the x by x of e to the j omega on both sides, and using the fact that y of e to the j omega over x of e to the j omega is the frequency response. So now this relates to what was asked earlier. Because it's the serial concatenation, we know that the overall frequency response is the product. Okay, so this was important, and this was, as I said, this was pointed out during the exam, just to make clear, because we had focused mostly on serial, so that's why I was a little bit sloppy, and I just assumed people would interpret it as serial, but that was made clear. And so it's the product, and so now it's a matter of multiplying through these. So you ought to be familiar with how to deal with, when you are taking products or even factoring things that are these polynomials in the variable e to the minus j omega, right? You can think of this as if it's a polynomial in e to the minus j omega. If we gave a name to that variable, if we called it like v, this would be 1 minus 1/4 v minus 1/8 v squared. So that's the overall frequency response. That's kind of the first part of the question. whoops. And then the second part of the question had to do with finding the inverse system. And so there we have to use, again, we're using the convolution property, the inverse system, the convolution property of the discrete time Fourier transform, just like for the continuous time Fourier transform, means that, there's h of n convolved with g of n is equal delta of n. When we transform that, it becomes this expression in the frequency domain. And so this related to the question that Natalie asked earlier, the frequency response of the inverse system is just going to be the inverse of the frequency response of the original system. Okay. And remember, the system we're talking about is that concatenation. So it's that system that had as its frequency response this thing right here, the denominator. So 1 over that h of e to the j omega was this quantity right here. So that's the answer. That's the frequency response of the inverse system. Okay, just 1 divided by the thing that we computed for the original concatenation system. And then the second part, the final part, was to apply this x of n, which is delta of n minus a half delta of n minus 1. So it's just 2 stems. Apply that at the input to the inverse system. And so for this, we used, we haven't really computed the frequency response, the impulse response of the inverse system. We've only computed the frequency response. And so we're going to do our work in the transform domain. So we're going to use the fact that we can compute the transform of that input. It's just delta of n minus 1/2 delta of n minus 1. Well, it looks exactly like something similar to the frequency response of the first system. It's actually just 1 over it. So its x of e to the j omega is 1 minus a half e to the j omega. That comes from using the time shifting property. So we use the time shifting property to get this. The output of the inverse system, which has the unknown impulse response g of n, unknown in the sense we haven't computed it, but we know the output's going to be the convolution of x of n with that g of n. And now we transform to the frequency domain where we know the transform of that impulse response for the inverse filter. We know that g of e to the j omega. So the transform of that output we're interested in, the y of n, is just the product of x of e to the j omega with g of e to the j omega. And as I said, it was rigged. The problem was rigged so that this x of e to the j omega would exactly cancel the h1 of j omega, which was 1 over 1 minus a half e to the j omega. So these two pieces cancel each other out. And what we're left with is just 1 over 1 plus a quarter e to the minus j omega. That's our y of e to the j omega. And now we can transform back using the inverse discrete time Fourier transform. So look up the pairs, and it turns out to be this guy, minus a quarter to the nu of n. Okay, so that's kind of a standard type of DTFT problem. Sorry, I didn't mean to knock that off. Are there any questions about that one? Okay. If not, I guess there's time for one more question, if anyone has one.
I guess could we go over Laplace?
Which one?
I think I don't remember which exam it was, but there was a Laplace problem that I saw. I need to check if I can find it. But any Laplace
Well,
problem
there was
would
a
be
plus
fine.
problem
Oh,
on
I think
pretty much
problem 5.
every exam.
Yeah, I think that for this one on 22, it's problem 5.
Okay. So which part? Any particular part? So you're given an h of s, you're given an LTI system with a given transfer function, and you're asked to sketch the pole zero plot. So you have to find the poles and the zeros. And then you're told that it's stable and you're asked about its frequency response, h of j omega.
Yeah, I'd say B and C were the main parts that
Okay.
I want to go over.
So that, this turns out to be the pole zero plot just by solving for the roots of the numerator and denominator. This is now the calculation of the frequency response. So here you have to use, that geometric technique that we talked about. So the h of, let me blow it up a little, h of j omega, the magnitude is going to be just, well, you plug in j omega into the h of s. And so you're going to get s minus 1 was the numerator, so you get j omega minus 1. And then the denominator factored into these linear terms, s minus this times s minus that times s plus 1. And so you plug in j omega. And so now you ask, what can you say about the lengths of these vectors? So here's, the numerator is the dashed blue line. It's the length of that vector, j omega minus 1. So it's the length of that vector in the dashed blue. The denominator is the 3 red vectors, the product of those. So you want to know how that product behaves. But when you look at this expression, the j omega minus 1 in the numerator and the j omega plus 1 in the denominator, right? That's this dashed blue line. That's the numerator. And the red line on the left, the j omega plus 1, it's this guy. They have the same length. No matter what j omega is, those two have the same length as each other. So they cancel out. So you're just left with the only thing that's left that you really have to think about is now the lengths of these other 2 red vectors. So it's this guy and this guy in the denominator. J omega minus that first pole and j omega minus its conjugate pole. Well, you can kind of, you're asked, that's the general form, but you're asked specifically about omega equals 0. So if you plug omega equals 0 in there, you're really looking at the situation where the two lengths that you're interested in are this length, because that's the j omega equals 0 point, and this length. And that's just, use the Pythagorean theorem to figure out what that length of that hypotenuse is. Just going to be square root of 2 because these are both 1. Both these lengths are 1. So that's where the square root of 2 comes in for both of those factors. Looks like there's a parenthesis missing here. It's square root of 2 times square root of 2. Or maybe the square root of 2 wasn't supposed to be there in the first place. Okay. So you get 1/2 for at 0, omega equals 0. And then the rest of the question is very similar, but you're trying to figure it out, I think, at the limits, at plus and minus infinity, as is usual for these types of problems. So you're just plugging into this expression, really you're looking again at in the denominator, it's the product of those two. You're looking at the product of the lengths of these 2 red vectors that were not canceled, these 2 red vectors right here, this one and this one. And so as omega goes to infinity, I guess that's actually the next, is it the next part? Yeah, the next part is going to infinity. You just see that it goes to 0 in both cases. Plus and minus infinity goes to 0. The other thing had to do with the angle. So you were also asked about the angles. So with 0, remember the vectors that we were looking at were these 2 vectors. So you needed to know what the angle of those 2 vectors was. But it's the angle of the, I'm sorry, let me go back a second. That's not quite right what I said. That I was talking about the, whoops, I was talking about the magnitude there. I want to talk about the angles specifically. So when you look at the angles, you now have to look at the angles of the numerator, j omega minus 1. So the angle of the blue vector minus the sum of the angles of the denominator, because we're using the fact that, you know, the angle of the ratio is the difference of the angles, and the angle of a product is the sum of the angles. So here's the numerator piece right here, and then minus the sum of the angles in the denominator, which is this piece right here. And so then you have to figure out what those angles are at 0, at omega equals 0. So you have to go back up to that picture and figure out when you're looking at omega equal to 0. Sorry, it keeps moving the thing that I'm clicking on so that it cancels it. The things we're looking at is the blue line is going to be this one. It's going to be this one right here, that angle for the numerator. And for the denominator, it's going to be the sum of the angles of these 3 vectors. I'm going to draw them in pink so you can distinguish them from the red. So there's going to be this one, and this one. And when you compute those angles, they turn out to be, you've got a pi, you've got, because again, remember, you have to remember that the vector is going from it's j omega minus the 1. So let me go back to the picture to give you make clear what the directions of these vectors are. The blue vector is going to be this one. So it's actually pointing to the left. The pink ones are going to be, they're all going to be terminating. The vectors terminate at j omega, which is, we're setting that to 0. So it's the angle of these 3 vectors. So the blue vector, it's a negative going one on the real axis that corresponds to angle pi. It's a negative, like a negative number. The one from -1 to 0, that's positive going. That's going to be angle 0. And then these 2 guys that come from the conjugate poles, one of them is going to have an angle which is, you know, you kind of have to position the vector so that it starts, you know, so one of them is going to look like this, and one's going to look like this. So this guy is, if we treat it as a positive angle, this guy is 3 pi over 4, right? It's 3/4 of pi. And this guy is actually, it's going to be, well, it's minus 3 pi over 4, but it's, if we write it as positive, it's going to be 5 pi over 4. So when we go down here, we end up with pi. That's from the blue guy. Pi minus the sum of, well, one of them was 0, one of them was 3 pi over 4, and one was 5 pi over 4. So when you add it all up, it becomes pi minus 2 pi or negative pi. But of course, negative pi is congruent to pi modulo 2 pi. And you can always give the answer modulo 2 pi. So the answer turned out to be pi. Minus pi would be perfectly acceptable too. Okay, so that was the answer to that one.
Okay.
All
Yeah,
right.
that makes more sense. Thank you.
Okay. Okay, everyone. Well, I'll see you all on Tuesday at 11:30, unless you've made other arrangements. And I'll be sending out, I had a few requests for changes on the seat assignments for left-handed tables. So I'll be sending out or posting the seat assignments later today, the final version. Okay. Good luck, everyone. I'll see you on Tuesday.
Thank you,
you.
Professor.
Have a good day.
Okay, bye-bye.
Thank you, Professor.
Thank you, Professor.